Okay, we are going to continue with circuit analysis. However, we looked at an example where, we looked at the bridge. We had our supply. And this is a bridge. Okay. We had a supply and we had our bridge. A little bit too long. Alright. Then though we say typically we take our load across like that, we say that I want to look at a scenario where we remember sometimes we have to think out of the box. Let's suppose we took a load out of on the perimeter, rather, any one of these other resistors. Let's call that R1. What would have been R1? Let me call it RL. Let's say I'll take it from there. That's my R1. That's my R2. That's my R3. That's my R4. So if you're going to do Norton or what you call Thevenin, we consider the one that is regarded as the load is the one that is susceptible to change, that may be changed. Okay, so now what we'll do is we'll say we know that, let's call our supply VS. We know that this could be redrawn. This could be redrawn like this, where I put that straight and that straight, and this is my positive and that is my negative. It makes it easy if the run is straight down. There is my RL, my load. There is mine. From the I take R1 from the positive, I take R out RL and R1. So my R1 also comes out of the positive. Okay, this is R1. Now these R2, like we had previously when it was the load, these R2 joins these together. Okay, this is R2, and from between R2 and R1 we have an R4 taking us to ground, to negative R4. Between RL and R2 we have R3. Between RL and R2 we have R3 taking us to negative. Okay, so this is what? R3. So, however, remember that if this is RL and we're going to analyze the circuit for Norton and Thevenin, we have to remove it from the circuit. So if we do that, we have to identify the points where it was removed, so we know this is the what? A, B. Nothing stops us from calling this X and whatever. Do you then see that when you look at this, it's like at the positive we've only got RL, and then these two here are actually in series now. Being in series, R2 and R3 being in series, they are still parallel to what? To R4. What does this tell us? It means now when I want the voltage across, because I need to know the voltage between these 2 points. But I do know, remember we said V, I would say in the case of Thevenin, VThev would be the voltage between those 2 points. Remember, with Norton, we are going to want I Norton, and we're going to draw a line there. We're going to draw a line with Norton, we're going to draw a line there. Let's start with VThev. VThev would be us breaking that line and then knowing those 2 points and wanting to know the voltage. VThev would be VAB. VAB, which we already said is what? VA minus VB. And the positive. Alright. well, well, the difference. All right. Now, if you look at this, then it means we have to work out VA and we have to work out VB. Lucky for us, we know what, but we know VA. VA is equal to the supply. When you measure that point, measurement is between that and negative, and that will give us the supply. So there we are measuring the supply. That's easy. So that VA is the supply. What we need to know is VB. How do we get VB? VB is, you have to realize that we have a scenario here where we've got R series 1 being those two resistors there, R2 plus R3. That is R series 1. But R series 1 is parallel, we'll call that R parallel 1. R series 1 is parallel to R series 1. R parallel 1 is R series 1 parallel to the 4 ohm resistor. So it's easy to get R series 1, we just add these two values here. To get that, when you've got that answer there, we can now do RS1 times RS4 over RS1 plus what? Remember that will simply be RS1 times R4 over RS1 plus R4. We've been doing this, so this should not be a problem. Alright, so however, our R total there, which will determine our current as well, if you want our current, our R total will be R1 in series with that parallel network. So it will be R1 in series with that parallel network, which is therefore, so once we've got an answer here, our RP1 is easy to just add to whatever value we're given is what is R1 there. So this computations cannot be that difficult. Now, however, we may need I total in this calculation, in which case it's easy. Whatever answer we get here is R total is simply V supply over R total. Why would this be important? Because we need to work out the voltage here. Now, to work out the voltage here at B, we can use the total current. With the total current, we can determine the VR what? Remember, when you've got total current, we can determine that total current is the current that will flow through R1. R not, let me see, maybe I will need space. Not, there is one continuous line through the circuit. This is just the positive line. There's one continuous circuit through R1. So I total here would flow there, and the same I total will flow through here. Okay, there's been no split yet. This is just a line, it's just a connection. There's no split yet. It's just saying this is a wire to the positive. So not I total is the same as IR1, which gives us IR1, which implies, let me rather say, which implies that we know VR1, because it will simply be what you call this I total or IR1 times R1. That will be easy. So it will give us that voltage there. Once we've got the voltage there, our life is easy. Why? Once we've got the voltage there, our life is easy. We can now apply Kirchhoff or Kirchhoff. Okay, I think I spelled it right this time. Kirchhoff's voltage law, or KVL, and the current law. You have to, in this case, the Kirchhoff voltage law. The voltage that is there and the voltage that is in the parallel network is what is going to give us the supply. So the total of that and that the voltage drops is going to give us the supply. So VR1 plus VR4, which is the same as the V through the sum of the two there, the voltage through this and this voltage through that together give us VR4. That VR4 or VR2 plus VR3, remember VR2 plus VR3 is equal to VR4. So that value is one value, is a parallel value. So this is V parallel, is the same value. So VR1 plus V parallel will give us V supply, which makes our life easy, because now we know what V parallel is. V parallel is simply going to, according to Kirchhoff, V parallel is going to be V supply minus VR1, and we've worked out VR1 through there, so it's not been difficult. Now, once we've got a value for V parallel, now these two guys are going to share. We want to know the voltage across R3. Why? B is across R3 and ground and negative. So we want to know the voltage at point B. It is the voltage across what? But VB, which we need it there so that we can know our what? Our VThevenin. VB is equal to the voltage across the R3. This is given by the voltage divider. There's two of them sharing V parallel. There's two of them sharing V parallel. So the value across R3 is R3 itself over the total R2 plus R3 times V parallel, which we know. Why? We've worked out VR1 from the total current. So I said we could use total current. So we know this value. So therefore that will be easy to get VB. Once we've got VB, that VB can be substituted in this formula. We know VA is the supply. So we substitute VB into this formula, and we've got our VThevenin. So that wasn't difficult. So what do you see here? Analyzing the circuit is very, very important. Okay. We could have said also another method, instead of worrying about IT, the alternative, this is where we've chosen to use this approach name. We could have said, okay, could we have done it a different way? When do you decide when to do what? How do you decide when to do what? Really, for me, I always go with the easiest option. That for me was easy enough, so I would have probably done that. So alternatively though, it's also easy. It's also equally easy. None of these theorems is difficult. It's equally easy to have said, but I have got R1, I have got R2, R3, I was given in the circuit. So I could have worked out R parallel. Okay, R series 1 I have, R parallel 1 I have worked out already. I don't have to work it out. I already worked this out. So I have already R series 1, which is these two, R2 and R3. We have worked out R parallel 1, which is these two in series but in parallel with that. So we've got a value for R parallel 1. So I could have said, instead of going through the other method of going of IT, I could have said, I know voltage already. I know that this here, R1 plus that is the total resistance there. So if I want voltage on the parallel network, this would have been much easier than the other method actually. Voltage in the parallel network is simply R parallel 1. We've worked it out, or in this case there's only R parallel, but because I always give it 1 in case I have to, in case I may find later another parallel network. Okay, so that R parallel 1 that we have worked out over R total, which we have worked out. So without having gone to what, without having gone to calculate what goes this, to calculate I total, we could have worked out our through the what, our V parallel through the what, through the voltage divider. Okay, so this parallel network over the total resistance will give us the voltage for the parallel network. The supply, sorry, will give us the voltage for the parallel network straight up. So now when we've got V parallel, we could have said, but these two share, we want VR3, which is our VB. One VB, which is VR3, is simply, we go back and say R what? R3 over the R series 1 there, R2 plus R3, a value we have already, times what? Times V parallel, a value that would have worked easily like that. So for me, this was the easy option. Two calculations would have given us that VP value. All right, so I'm saying you could use either method. You could have gone on and calculated IT, but then that, for me, that would have been unnecessarily longer, and then probably you make a mistake in that calculation, then you come the rest of what you're doing is a waste of time. Whereas two straight calculations from what you've done already could have given us what, our answer straight up. So I wonder whether this helps. However, this only helped with what? With the working out of the what? Of V Thevenin. If we're going to do, well, this is a video, so people can stop whenever they want to. If I was a little bit fast, they can replay, and they can also go back and check if probably they didn't understand something. If we're to do what call this just start there. If we're to do the resistance, yes, okay, the resistance, we will simply have said we replace the source with an equivalent resistance. If we are given a value, we put that value there. We're not given a value, so we put a what? We put a wire. The resistance is 0. We assume 0 if we're not given an internal value for internal resistance. Now we say we must run from A to what? To B, and see what the resistance there between those 2 points is. So now I always want to start with a straight line and say this is my A. I start from A. From A, I've got two. This whole line is now A. This whole line is now A. So if you notice, I've got one way of leaving A, and that way is what? Is through R1. Okay? But notice this. I won't start with R1. Why? It's going to take me to a lot of places. Notice how leaving A, this whole point is A. This whole line has now been joined together. So this is all A. Now, I could go straight to B via R3. So for me, since this takes me straight to B, I'd rather start with that and say, you took me straight to my B. So one route is straight from A via R3 to B. However, there is another way of going through, and this is the first one there, R1. Or, alternatively, there is three ways of leaving A. R1, R3, and R4. So, I could have left A via R4. So, I draw all scenarios of leaving A together. Now, look at this. If I leave via R1, I join up on the other side with R4. So, the R1 and R4 actually join up. Okay, all it tells you is that R1 and R4 are actually parallel. Okay, they are connected on the one side and they are connected on the other side. Okay, once they are connected on the other side, they connect to R2. And voila, R2 takes us to B. So, what does it mean? See, proper circuit analysis makes our life very easy. It means these two are in parallel in series with R2, the whole set in parallel with R3. What does it mean? It means we must work out R Thevenin, and remember Thevenin and Norton are work the same, or R Norton, the resistance is work the same. These two can be worked out from what? From R1 being parallel to R4, that set being in series with what? Being in series with R2. Okay, so that is this part. All right, these two in parallel, but together this is parallel to R3. What does it mean? It simply means get a value, work out these two, R1 times R4 over R1 plus R4. That gives you, let's call it R parallel 1. We had R parallel 1 when you're dealing there, so I'll probably call it R parallel 2. See now why I named them different. Now this R parallel 2, because remember when you were doing the what? The voltage, we had R parallel 1 already. Okay, so now I'll call this R parallel 2. When we're not doing what? We're not doing the resistance. I can't call it R parallel 1 and then there's and then there's two R parallel 1s. It can not only can get confusing, it's mathematically wrong to have two things that are identical things that are actually different. Am I making sense? Identical things that are different. Really? So if you cannot have R parallel 1 twice and yet they are different. Okay, their values are different. So I would call it this is a different scenario from that. So this is a different R parallel 1, R parallel. So it's not R parallel 1, it's R parallel 2. So after you've got R parallel 2 there, you will say, but our R parallel 2 needs to be added to this one. Okay, and we are going to call this R series 2 because we have series 1 here. So I'm going to call that R series 2. This one here is going to be added. Whatever value we get here, the parallel value we get here is going to be added to that, and that's R series 2, and that is parallel to R3. What does it mean? It means let, what do you call this? R parallel 2 plus R parallel R2 be called R series 2. Why? R series 1 was taken there, right? So then we have, therefore, at the end, what do we have? Therefore, our R not 1 or R Thevenin, because it's worked the same way, would then be our, this, remember, this is now R series 2. This will therefore be R series 2 R series 2 times R3 over R series 2 plus R3. So with values, pop, you've got your answers as easy as ABC. So I don't know whether this is too, I mean, I think if you, what you would realize is after analyzing your circuit nicely, this becomes very, very easy. I don't think, as long as you can analyze your circuit and see exactly what's what, I think this is not difficult. I think the where people lose it is in realizing, in analyzing these circuits. That is where people actually get lost. Now I don't know whether I need, because it does not matter. If I were using that as what? As RL, right? If we were using that as RL, remember you can pause and really get a thing until you understand. So I don't have to pause because the time is going to kill us. The video is going to be too long and end up losing you in the process. Now, if we had this as R4, I need to remove that. If we had this as RL, and that is R4, things will be different. If we remove this one, because remember, we remove the one that we call the load, the one where that is changeable, all right? So because the loads can change, so we would have called that point and that point, doesn't matter which one, A and B. Okay, now if we did that again, when we work out the voltages, for me, I always say, if you are not sure, redraw and make your lines straight. Skew lines can confuse some people, not everyone, but if you are one of those that it would probably mess with, you just redraw and make your life easy. Okay, so that there, from the positive, we now have R4 coming down, and we've got R1 also coming down, and then the R1 is now continuous with R2, R1 is continuous with R2, and they join on the other side with R4. Okay, they join on the other side with R4, and once they've joined, they continue to the negative through R3. Okay, so now you can see this is easy. That's your series value. Once you've got your series value, you can make out your parallel value. Once you've got your parallel value, you can make out your total. So I'm just saying, once you, and now where is the point? There is your point A. Okay, so just to say we are here, let me just think that we would want to say we first have this is our point A. Where's our point B? Our point B is anywhere on the negative. So that is our point A. But for voltage sake, this is our V supply. Our voltage here is a little bit trickier. It's not as easy as it was before. Our voltage here is a little bit trickier. It is the voltage across this plus the voltage across that. Remember, according to Kirchhoff, the voltage here is obviously, after dropping this from the supply, whatever's left is left for these two. Okay, so the voltage across this and the voltage across that is together will give you VA. So VA will be VR2 plus VR3. Okay, need to be careful there. Now, how do you where do you start? It will be, for me, it's easy to start with the series resistor. R series 1 would give us R1 and R2. Okay, once we've got R series 1 is parallel to what? Is parallel to R4, so we can have R parallel 1 is equal to R4 parallel to these two, but these two are R series 1, which will give us R4 times R series 1 over R4 plus R series 1 with values on your calculator, and those values are easy. Right now, once you've got that value, you've got a value for RP1. Your R total therefore becomes R3 plus R parallel. Remember, this is R parallel 1. Okay, so that will be plus R parallel 1 because that is in series with that parallel network. Okay, so that will be R total. Once we've calculated this value are given, straightforward calculator P, you've got your answers. Remember to store your answers. Remember not to use rounded off values in subsequent calculations. Now you've got your values there. What do you want? You are actually looking for voltage. We have the voltage at VA. What do we do? Because remember, VTEV is still equal to VAB, which is still equal to VA minus VB. Okay, so we know VB, but we know VB. I'm having traffic issues here. Also, we know VB equals to 0 volts. Why? VB is on the negative. All right, so we already know VB, so we don't even need this. Whatever we get as VA is actually our VThevenin, meaning this here means VThevenin, i.e. VThev equals to VA, because VB is 0, right? So if you subtract 0, so VA, when we work out VA, we've got our VThevenin. This is a nice scenario. Only that it's a little bit tougher to work out what the value now, because we have to get two values and add them up. Now that we've got this, we can work out that very easy. Okay, how do we know that value? That value is what? That value is R3, VR3. Do I need to do that? I don't really need to do that. I can, no, I don't need to do that. I can, there's no harm. I can do VR3. VR3 is equal to R3 over R total. I'm trying to run away to say maybe we're running away from something. No, I'm not running away from anything. I just think it's not the cleverest way of doing things. But we could have done it and said times V supply. We are sharing that over the whole total times V supply would give us VR3. Now to get V parallel, we would have to say V supply minus VR3. This is what? This is Kirchhoff. If we remove this, what is left is for the parallel network. That is one way of doing it. But for me, it was cleverer and quicker to have simply said V parallel is equal to an R parallel we know we would have done this calculation once. This calculation, only that we have R parallel here, over R total times V supply. And we would have had our V parallel straight up. So we wouldn't have had to do two calculations like this. That's why I was saying, let me not fuss about VR3. Then I said, okay, but you can do it. But if you do it, it's only going to be a longer run because you need two calculations, whereas one calculation with values you have already, or in this case, V parallel is actually R parallel 1. Remember that we are what? We might have another parallel, okay, later. We will have another parallel when you're doing what? When you're doing the resistance. Okay, this is the voltage part, so it's one parallel value. So this would have taken us straight to the answer. That would have taken us two steps. So not really a major difference, but yeah, there's some ways of there are many ways of killing a cat, but some ways are cleverer, some ways are more human than others, So I'll put it like that. So now, if we then look at how do we get VA now? Once we have V parallel, R1 and R2 are sharing V parallel. So you simply say but we need VR2. So simply say VR2 is equal to R2 itself. R2, but I'm writing 3 here. R2 itself over the total, the two that are sharing, R1 plus R2, that times V parallel, a value we have here. So once we do this, we multiply with that value that we've got here. Remember, memories, please recall your answer from some store. You have stored your answer somewhere. Recall your answer from what? From that store. Do not use random figures in calculations. If you do that, you are veering off your answer. Ultimately, after 10 or so calculations, you are so far off, you can't even see your own back. So now, this here is how you get VR2. Once you got VR2, we go back here and we get VA. Okay, remember we started with what? Oh, okay, we didn't do, maybe it wasn't bad to calculate that because we need it here anyway. But again, another way, you see, the thing is, when you talk, sometimes it's a little bit difficult to think while you are also, you have to, sometimes, people might talk of multitasking, but sometimes when you talk, your brain is not totally focused on your actual thinking. We could have actually made our life easier by just calculating R1. When you calculate VR1, which would have been easy, VR1, because after we got VR2, we still need to what? To know that value that I cancelled. So probably me cancelling this one was not a clever idea. Maybe just offer it as an alternative. Okay, that, or maybe offer it as an alternative, or because if you had done this, you need this VR3 here to come here and say, remember, our VA is VR2, what you just got here, plus VR3, which is what you'd have got there. So maybe there was no short here, but I'm still saying this was me not at my best. At my best, I would have said, why bother with all that? I will calculate. Once I've got, I would have not done this. Yes, I would have done that. After doing this and getting V parallel, I would not have calculated that one. I would instead have calculated VR1. Okay, once I get VR1, I will say VR1 is actually R1 over the two that are sharing that parallel value, that is R1 plus R2. The two that are dividing that value times V parallel, which I would have done here. I would not have done this, I would have done this, then I would have gone on to do this. Then once I've got that value, because it takes me straight to a value, that value is calculated, that value there, it will take me to VR1, and I'll say, therefore, VA is equal to V supply minus VR1. Okay, because once I've got that value, it is the value at that point is that supply minus what was dropped at R1. So that will be what? That was actually, for me, it would have taken this calculation, that calculation, 3 calculations to get to the answer. So for me, that would have been a clever approach. But I'm saying, I give you all these alternatives, whatever works for you is fine. You could have done this. After doing this, don't worry about this. After doing this, you've got your VP. You come and do your VR2. Now you take your VR2 and you add it to your VR3 that you've worked out here, and you've got your VA. Or you could have done this. Once you've got that, you go ahead and work out VR1. Once you've got VR1, you subtract your VR1 from your supply, and you got your VA. So it's maybe I would say this or that. Okay, this top one or the bottom one. All right. So I don't know whether, isn't that nice? Is it? I prefer nice stuff. Prefer it to be nice. So I would say possibly make it nicer, a little bit smaller, and move it up, and then draw a nice straight line between the two. Say maybe you could have done this calculation or the other calculation, but anyway, I hope the whole point is for people to understand, not to try to show how smart we are or how not so smart we have been. All right, so I hope you got the gist. This is basically you'll see that if you can't analyze circuits properly, you would actually struggle with working out your VThevenin and your V Norton, your not V Norton, your VThevenin and your R Thevenin or R Norton. So far, resistance is common between the two. VThevenin is actually easy. The other thing that I'll explain maybe in the next session, in the final session, I'll explain the Norton the Norton current. The Norton current, that thing of the line sort of confuses people a little. So I hope this covers a bit of mileage in our courses. Thank you so much.